Well, this is the sixth presentation on the structure and properties of organic molecules. We've been focusing in on neutral structures. Our first video or presentation looked at taking simple, molecular formulas such as C4H6O and building all possible structures for a molecular formula, given what we know about Lewis theory and Vesper theory, how to connect carbons, nitrogens, oxygens by the rules that carbon has 4 bonds, nitrogen has 3 bonds, oxygen has 2 bonds. That's Lewis theory. Vesper theory, setting atoms in particular places around the bonding based on valence shell, electron pair repulsion theory. Now, of course, if we were to look at something like penicillin, where R is not defined here, and there are different types of penicillin, we certainly could say there are probably more than 1,000 different ways in which you can connect all the atoms that we have here, along with the degree of unsaturations that we have. We have one here, one here, one here, and we have 2 rings, so that's 5 degrees of unsaturation. There would be I can't say infinite, but a significant number, above 1,000 different ways in which we can make a constitutional isomer of penicillin. So certainly, as we go on into organic chemistry, there are molecules that we'll have to consider as a starting point to discuss its properties. But when we began this journey through structure and properties of organic molecules, we started with simple molecular formulas and built a smaller number of molecules because there are fewer number of carbons and hydrogens and oxygens, and we had a number that we could manage, maybe 5 to 10 structures that fit a certain molecular formula. So that was our first presentation. And then we had duos. We had the theory of hybridization based on orbital theory. It was a modification of orbital theory developing around the 1930s. And then we covered the practical applications. How do we set hybridizations for carbons, nitrogens, and oxygens within a molecule? So we have on the side here written some rules. sp3, well that would be for carbons that have 4 single bonds, or oxygens or nitrogens that have 4 single bonds. Most oxygens and nitrogens, though, are only going to be in, 2 bonds, whether it be a sigma all around this nitrogen or a pi and a sigma for this oxygen. And we had rules for pi bonding that if it's 1 pi bond, it's sp2, and if there was one atom in here that had 2 pi bonds off of it, it would be sp hybridized. And the important thing is to be able to tag those hybridizations. For example, this oxygen, it's sp2. That's not enough. We know it's needed to move from hybridization to a picture that we actually see the hybrid orbitals holding these 2 lone pairs, and we see a p orbital coming straight out towards us and bonding with a p orbital on this carbon to give us a pi bond. That's just the sp2 view of this oxygen, seeing 3 hybrid orbitals coming off this oxygen, 1 overlapping with this carbon and 2 holding lone pairs, and then a p orbital coming straight out that's overlapping with a p orbital on this carbon coming straight out. So that was our 2 videos or presentations on hybridization. Then we had 2 videos on resonance forms, drawing those for cations and anions, but then knowing how to draw resonance forms for neutral structures. And from this point, we're going to pick up with acid-base chemistry. So I want to just do a quick review of the 3 boxes here: drawing structures, orbital hybridization, looking past letters and lines, and then drawing structures. Resonance forms, for neutral structures. Let's review real quickly what those steps are. Drawing structures from molecular formula, we need to get to the degree of unsaturation, determine the number of pi bonds or rings you have within any structure that fits this formula. Try drawing frames, carbons being on the inside and halogens being on the outside. If we have oxygens and nitrogens, they can slip into the framing for the structure. Then filling in with pi bonds that can be set to different places, pi bonds and halogens that can be put on the framing of the carbons and oxygens and nitrogens that make up a particular molecular formula. And then we had seeing past letters and lines. So yes, so what? We can build a molecule, but we need to see past letters and lines. We had rules for setting hybridization for C's, N's, and O's. 4 single bonds, sp3. 1 pi bond, sp2. 2 pi bonds, sp. If it's an O or an N that's not in a pi bond, and it doesn't have 4 single bonds off of it, we had to consider resonance or maximum separation. Max separation, SEP. We had to consider those two. Resonance trumps maximum separation. When did we have it? When the O or N is next to a pi bond. O or N that's next to a pi bond, we said, oh, by resonance it's sp2. That's generally the case, sp2. So those are the ways in which we set hybridization for nitrogens, oxygens, carbons. Now finally, focusing again on neutral structures. We're going into acidity and basicity of neutral structures. How sensitive is this neutral structure to a base, and how sensitive is the neutral structure to an acid? So we need to remember this. If heteroatom is next to a pi bond, then it is partially positive. Why? Because it's donating by resonance its lone pair to the neighboring pi bond. So remember, O or N next to a pi bond, it's a pusher. It's partially positive. We called that a pusher. So I'm just going to say it has a push. Pusher. If heteroatom is in a pi bond, so the example being something like this, not something like this, then it's a polar. It has a partial negative charge. Why is this important? Because in coming to the question of how does this molecule react to bases and acids, we need to find where are the most acidic protons, things that would react with hydroxide coming in at the neutral structure, and where is the most basic site, something that would react with a proton in that molecule. So for example, let's go back to penicillin. We can ask, if I put a proton in the solution with this molecule, where would it most likely grab that proton? Where is its highest propensity going to be as a site to grab that proton? Well, let me ask, what charge are we going to need to look for in this neutral molecule? If we're trying to grab a positive, I hope you're saying, well, I'd need to find a negative. Is there a full negative in this neutral molecule? No. But there are love handles, there are partial charges, and we need to find them. And it's not that all O's and N's are partially negative. By resonance, this is partially positive. It's donating its lone pair electron density to the pi bond. We know that now. This nitrogen is partially positive. It's a pusher. It's pushing into this oxygen, making this oxygen partially negative. Now there's a unique feature of a penicillin molecule that gives it its special reactivity in the body. This is a beta-lactam ring, and for purposes we'll learn later, this nitrogen is actually sp3. It's unique. You would say it's a lone pair next to a pi bond, like this one. It should be partially positive, but it doesn't give its lone pair electrons through resonance to the neighboring pi bond. It doesn't delocalize in. It's sp3. It actually turns out to be partially negative, and that is the site of greatest basicity within penicillin. If I put a proton in with penicillin, it protonates this nitrogen. It's partially negative because it's sp3. It's not partially positive due to resonance donation to the neighboring pi bond. There's going to be more on that in future recordings. But I do know this proton would not go here or here. These are partially positive just by our rules, and the oxygens would be partially negative, so it would have to be down to at least these three. Oh, sorry, this one also would be partially negative. So we have all these oxygens in pi bonds. They're polars, partially negative. And this sulfur would also be partially negative. So it has to be between these four and this one, special one. There'd be 5 places that we'd have to consider as possibly interacting with the proton, this acting as a base. Okay, that's one issue. looking at how it reacts with a proton. But folks, it's not the same question as how does it react with a base. We can't just say it's the opposite. You have to consider these two questions of how does it act in an acid solution, acting as a base. How does it behave in a base solution? It would act as an acid. How does it behave with a base? That's different from the question of how it reacts with an acid. So let's consider how it would react with a base. If it's negative, we'd be looking for partially positive charges within penicillin. And those have been noted here. Partially positive nitrogen, partially positive oxygen. These two sites and protons around them are very susceptible to attack. So we'd say it's got to be one of these two protons that would be most susceptible to a base. Do you notice then that had nothing to do with the site of basicity towards an acid? Please, it's two different questions. I call this Monday question and a Tuesday question. Monday's not part of Tuesday. They're two different days. Considering how a neutral molecule reacts with a base or an acid is two different questions. Well, let's go into the question of how does this act as an acid? How do neutral molecules act as an acid? How do they react with Monday, the base? If I had a base coming in and I'm trying to find the most acidic proton, where would I find that in penicillin? How do we approach that kind of question? Well, let's look at that. Well, to get some things out of the way, what is an acid in general? Well, we know an acid in the Bronsted-Lowry definition donates a proton, an H+, to our base. So we're saying this neutral molecule, our penicillin, is donating a proton to our base, in this case water, but it can be a stronger base, hydroxide. So we have a strong acid generating its proton to a weak base. So we can certainly have an organic molecule donating its proton to a strong base. Organic molecules are going to be weak bases. They're organic. This is an inorganic acid. Sorry, weak acids. Organic molecules are going to always be weaker acids than inorganic structures like HCl. These are always strong acids. So sometimes we'll have to make this act as an acid by using a strong base. But the action's the same. Bronsted-Lowry view of an acid-base reaction is that we donate a proton, here from HCl, to the base, which is water, or donate a proton from the organic molecule to a stronger base like sodium hydroxide. Transfer of a proton is the key idea when the action is called the Bronsted-Lowry acid-base reaction, transfer of a proton. We can measure, I'm not going to go into this in any great detail, we can measure the propensity to transfer that proton by taking our HCl or our organic molecule and putting it into a solution with water and seeing how much of the dissociation occurs, how many molecules break up to give the proton to the water and give us the conjugate base. A measure of that can be the K or Ka, where if we set the water at a high concentration to the amount of whatever we're testing as an acidic structure, if we set this really high, its concentration can be fairly constant, and we have a new K, what's called a Ka. And if that's really high, like let's say 1,000 is our K, then we're going to have what they call pKa, the negative log of that, which would be with 10,000, it would be -3. So we can say, hey, if we have a very high Ka, this is important, a very high Ka, very large, a lot of product, the acid's strong, it leaves very little of the original structure we're considering as a possible acid. It leaves very little of that behind. It's 1,000 to 1. Then we would say we have a very low pKa. The value is very low. So -4 is associated with an acid that has 10,000 over 1 product to reagent ratio. That would give us a pKa of -4. So just remember, Ka is high, pKa is low. That means we have a strong acid. And the stronger an acid, the weaker its conjugate base. So, for example, HCl, its conjugate base chloride is a weak base because this is a strong acid. The stronger a base, the weaker, in the opposite way. If we have a very weak acid, then we have a very strong conjugate base. So for an example of that, we could say H2O, sorry, let's get the base. The hydroxide is the conjugate base of water. If water is a weak acid, its conjugate, hydroxide, is a strong base, and that's certainly is the case. Water is a weak acid. Its conjugate is a strong base. Just one more thing to cover before we move into a qualitative understanding of acidity. The definition of acid is sometimes considered a Lewis acid. You'll hear that description instead of a Bronsted acid. Lewis acid is more inclusive of all acid-base reactions, but there are certain types of structures we call Lewis acids because they don't involve the transfer of a proton, but there's still a binding of the positive site to a lone pair. So in this case, a Bronsted acid, we still have a proton being accepting a lone pair. For example, down here, HCl gives a proton that is accepted by this oxygen to make a hydronium ion. So the Lewis definition would look at the lone pairs. The Bronsted definition, we have to consider a proton. So if it's a Bronsted acid, we usually call it such because there is this acid giving a proton to some sort of base. But if there is no proton transfer, we can still have an acid-base reaction. It just has to be outside of that circle wherein we involve a proton. We have some structures, and these are the typical ones that have aluminum or boron in them. And these aluminums and these borons can accept a lone pair. They can accept the lone pair and are considered then as Lewis acids because they are accepting a lone pair and there is no transfer of a proton. Just for fun, this is sp2 hybridized. We know that because there's nothing else off of borane, BH3. And that then tells us we have an empty p orbital that is sticking straight out towards us. If these are shown in the plane, we have our clover leaf that we know is the look for sp2 hybridization. There's an empty p orbital poking straight out towards you. That's what we fill up with the lone pair. All right, and the last two pages are going to look at more of a qualitative view of acidity of a molecule. So please, I know we have HCl, but we could consider just methanol, anything, as a possible molecule that interacting with water dissociates to make some of the conjugate acid and the conjugate base. Sorry, some of the conjugate base from this acid. This is a strong acid, but we could consider methanol with water and how much of that dissociates to form methoxide, OCH3- plus H3O plus, and that would be, I guess, a measure of its acidity. If we could find the pKa value for that, we could have a sense of how acidic this proton is. But what if we don't have pKa values? How do we still look at organic molecules and have a qualitative sense of how acidic that proton will be? Well, we use an acrostic. This comes from David Klein in his books, Organic Chemistry as a Second Language. Just remember the ARIO acrostic. Atom, resonance, inductive effect, and orbital is going to be used as we look at the conjugate base of the acid, the possible acid. We're always going to have to consider, when we're talking about stability, not stupidity. Stability is also the way we fill this in. We're looking at the stability of the conjugate base. That is key. This is key. If this is more stable, then this is a stronger acid. If this is less stable, this is a weaker acid. So you're really looking at the stability, not of the starting neutral molecule, but you need to consider the conjugate base. Draw the conjugate base and then apply the ARIO acrostic as you look at the stability of the atom with negative charge. As you look at the stability of the atom with negative charge delocalized by resonance to other atoms. As you look at the negative charge on an atom, that might be on a carbon that has a lot of fluorines off of it. That will help pull the negative charge away. So you're focusing in on the negative charge and you're applying what we call the areoacrostic. What's the atom that carries that negative charge? Is there resonance delocalization of the negative charge? Is there some inductive effects that help pull that negative charge away from the atom? And lastly, the atom that has a negative charge, does it have sp hybridization versus sp3? If it has more s to p character and sp hybridization versus sp3, it would be more stable. This would be more stable than a lone pair on an atom that's negative, that's sp3. The more s to p character, the more stable the orbital. That's the last consideration. These are put in order of significance and consideration. A, R, I, O. And there are some exceptions to the order of significance, but usually A and R are the most important issues in trying to determine the stability of the atom with the negative charge. What atom is holding the negative charge, and what is the number of resonance forms that help to localize the negative charge. So I'm just going to focus on these two, A and R, and then we're going to go ahead and go to a problem. So NH2 is less stable than NH2 amide is less stable than hydroxide because the atom carrying the negative charge, here the O and here the N, are different. Which one's more electronegative? O or N? More electronegative. I hope you're saying it's the O. So this would be more stable than the nitrogen, and that's how this reads. Amide is less stable than hydroxide. Hydroxide is more stable, so we would expect the conjugate acid, water, to be more acidic than the conjugate acid of amide, ammonia. This would be more acidic. Resonance. We can look at taking water and comparing its acidity to that of acetic acid. And it may be in the name, but we can take that proton off. The negative here would have resonance delocalization between two oxygens, so we're using two good atoms. Here, if we take this proton off, we have an O with a negative charge, and that's certainly better than an N with a negative charge, but I match your O, and I have a second one through resonance. So this would be more acidic than water. That's how we kind of use A and R to determine qualitatively relative acidities of molecules or even sites within one molecule. So going back to aspirin, we could say, hey, I need a proton on the right atom that might be most acidic. I'm looking for O's and N's because they're electronegative. Well, here's an O with a proton. And if I take that one off, the negative charge here would be delocalized between two oxygens. Ah, that's my most acidic proton that would come off in base solutions. What would be the second most acidic? I hope you're looking at this one. This would be first, and this would be second in acidity. Because here it's an O with proton, the atom is better. Here it's an N with proton. But at least this one has the localization by resonance to an oxygen. So sometimes what we'll do is we'll say this is a O-O combination, this is an N-O combination, and considering A and R an O-O combination for the negative is better. All right, now I want to move on. Just want to say, in general, having a lot of fluorines, that's the best type of halogen, on the anion, the conjugate base of your potential acid is always good. It stabilizes that conjugate base. So it makes the structure, the conjugate acid of this would be trifluoroethanol. That would be a stronger acid than the conjugate acid of ethoxide. And again, we've already covered orbital. Having an orbital that carries the negative charge, being sp, is better than having that orbital that has the lone pair on the atom that's negatively charged. It's better if it's sp hybridized than sp3 hybridized. All right, sterics is one of the least considered factors in acidity, but it is important. Basically, if it's a less hindered anion, it is more easily solvated. And that's something that doesn't get as much attention in discussion of acidity. Let's go to a problem and apply what we've learned. So we have four structures. How do we determine which structure is most acidic? You have to look at the conjugate base. So I'm going to go ahead and draw that for this ethanol. You say, well, how do you even propose a conjugate base? Well, we know a CH bond is not going to be broken because it'd leave a negative on the C, and that's the wrong atom. So we're going to try and win. We want to win against these other three. So propose CH3CH2O minus, because we're, again, taking a proton away from this structure. We want it to act as an acid. We want it to act as a Bronsted acid, so we take a proton away. So this is what we would have as conjugate base. Down here, sort of following the pattern, the N would be the best place. Oops, just one left now, and we've taken the proton away. We've given it to the base in solution. That's tearing off these protons. C, we'd propose as our conjugate base the acetate anion. Why? Because we want to go to an oxygen that has a proton, found it, and we want that oxygen with the proton, if it's next to a double bond, to be considered. Not a CC double bond. A CN or a CO double bond is going to give us stabilization by resonance. So we have that. O can delocalize its negative charge to this O by resonance. Well, here we're kind of stuck. And really there's no good choice. There's not much of a difference between the acidity here and the acidity here. There can be arguments made for either one of the possibilities. I'm just going to draw this one. Could we have drawn another one? Sure. We could have put the negative charge here as we tear this proton off. I think we can safely say, though, this one's the least stable of all four of these. Why? Because it's a carbon that's carrying the negative charge, and that's least electronegative. So this would be the weakest acid. All others have a better atom carrying the negative charge, O, N, and O. So we're now up to the other side. What would be the strongest acid? Which of these would be most stable, A or C? Well, it's an O to an O, so that's an O-O combination. Here we just have an O carrying the negative charge, so this would be the strongest acid. Second would be our ethanol, and the reason this is a little more acidic than ethylamine is because it's an O versus an N. O being more electronegative, this is more stable, this is a little less stable. This would be third in acidity. Well, that's it. That gives you an idea of how we can use the areoacrostic to predict relative acidities of four different structures, or, again, how you can simply look at a single species and find sites of acidity. We pitted these two against each other. This would be more acidic as a proton in penicillin than this proton. Well, that's a lot to chew on. The next presentation will be much shorter. We'll be looking at just the other direction, a different day, Tuesday. How would these respond if they're taking a proton, acting as a base, not giving up a proton? That's a different day. That's a different question. Bye-bye.